Hey physicists, what's the crack? So today we're going to do some paper-free section B on astrophysics. Okay, so we're going to look at Wien's displacement law. Okay, so what I have here is I've got intensity of my two stars against their wavelength. And the question wants me to find out about the temperature and the color of the stars. So it's a 4-marker. So the first thing I know, anytime I've got wavelength and I see temperature, I think about Wien's law. Okay, so Wien's law from my data sheet tells me that the wavelength maximum times by the temperature is always equal to a constant, which is 2.9 times 10 to the negative 3. Okay, so if I want to find out what the temperature of these stars are, all I need to do is 2.9 times 10 to the negative 3 divided by whatever the wavelength max is, and that'll give my temperature in Kelvin. Okay, so to find the wavelength max, I look at my first star, which is my solid line. I see its peak. So what I do is I take the peak down, and when I have this on my exam question, I could figure out that that number, just lower than 500, that ridge would have came out at wavelength max of 410. So it'd be 410 nanometers times 10 to the negative 9. And then when I look at this peak and I took the number down, in the exam question, it's just hard to put it on the graph here, but in the exam question, that number there comes out at 660. So 660 times 10 to the negative 9. So for this one, the temperature is going to be 2.9 times 10 to the negative 3 divided by 660 times 10 to the negative 9. Okay, so when we divide these two numbers to find out what this temperature is, you get 7250 Kelvin. And earlier, when I divided these two numbers to get the temperature, I got the number of 4,400 Kelvin. Okay, so straight away, we can see that the solid black line has got a higher temperature than the dotted line. Okay, so next thing I want to know is, it says, I want to know what about the color of these stars. Okay, so I remember my rhyme, which is, oh, be a fine girl, kiss me. So again, that tells my spectral class of the stars. So oh, be a fine girl, kiss me. O class stars are around 50,000 degrees Kelvin. Okay, you need to remember these numbers. The way I remembered it is you start at 50,000, you divide by 5 to give you an A class star, which is your 10,000 degrees. And again, divide by 5 again to get 2,500, which is approximately the temperature of an M class star. The only other number you need to remember is by our own sun. And our own sun is a G class star. Oh, be a fine girl. I can't even do my own rhyme, sorry. Oh, be a fine girl, kiss me. So our own class star is a G class star, and that's roughly around 6,000 degrees Kelvin. Okay, so I have here is 7,250, so that's hotter than the sun, so it's going to be in here. And then the dotted line for my other star is 4,400, which is slightly colder than our own sun. So the spectral class of this star is probably a K class star. And the spectral class of this star is likely going to be an F class star. Okay, next thing then, like we just said, is we're looking at the color. Okay, if I look at the sun with my own eyes, I know that its color is yellow. Okay, so this star is cooler than yellow. Okay, so anything cooler than yellow, you're approaching your oranges and your reds. So because it's slightly cooler than yellow, this is likely going to be an orange star. And again, this one is hotter than yellow. So again, anything hotter, or white hot is the hottest you can get. So hotter than yellow is going to be our white stars. And then just for revision, hotter again, the whiter is our blue hot. The way to remember this is think about key stage 3 and those Bunsen burners. The blue flame is the hottest flame. Okay, and then that orange, that glowy flame around the outside, the sooty flame is one that's less hot. Okay, so again, just because we're slightly hotter than yellow, the color of this star, my F class star, is likely going to be the color white. Okay, and that's your 4 marks. So that's grand.